Let's analyze the reduced row echelon form of an invertible matrix a little more carefully. So suppose we have an invertible matrix. Actually, we're going to assume something a little bit less. Let's suppose that we have a matrix A where there's some matrix B so that the product of A and B is an identity matrix. And let's see what we can figure out about how that affects the reduced row echelon form of the matrix A. Now, this, of course, A being invertible is just a special case of this situation, because if A actually is invertible, then the inverse of A will be playing the role of B. But, you know, it's possible to have a product be the identity matrix with B not being an inverse, or with A not being invertible. So let's see what happens. Well, let's call the reduced row echelon form of A, let's call that matrix R. So this is the reduced row echelon form of A. Okay, now we know a few things. So on the one hand, A times B is an identity matrix of an appropriate size. That's just part of the assumptions that we made. Also, because R is the reduced row echelon form of A, that means, right, if you start with A and you do row reduction, you get the matrix R as reduced row echelon form. But this row reduction, we can now interpret row reduction as doing or multiplying by a series of elementary matrices. So maybe you multiply, or maybe the first row operation is a matrix E1, and then a matrix E2, and so on, up to maybe there are k row operations that you have to do to get the reduced row echelon form of A. So this gives us R because we started with A and we did all the appropriate row operations to execute this row reduction. So the result is R. Well, let's call this big product of elementary matrices E. And something that we know about E is that E is invertible. And the reason we know this is because we can write a formula for the inverse. The inverse of E is E sub 1 inverse times E sub 2 inverse, and so on, all the way out to E sub k inverse. Now we can just check, right, so since all of the individual elementary matrices are invertible, this product on the right definitely is well defined. So the question is this really an inverse for the matrix E? But we can just check that, right? We can check if you start with E inverse and you multiply by E, do you get the an identity matrix of appropriate size? Well, this formula that I've written for E inverse is E sub 1 inverse out to E sub k inverse. And E itself is E sub k out to E sub 1. And you can see that, well, these are going to cancel and give you the identity, but then the next pair is going to multiply to give you the identity, and then so on, until all of these have multiplied to give you the identity, and you're just left with the identity. And the same thing happens if you multiply these the other way. Right? All of the elementary matrices hit their own inverse and leave the identity matrix, and everything disappears in a puff of inverse matrices, I guess. So, so this formula is verified, and that means that this supposed inverse for E really is an inverse for E. Okay, so we have an invertible matrix E, so that E times A is R. Let's take this equation and multiply both sides by B. If we do that, we get E times A times B, multiply on the right by B. So E times A times B equals R times B. Okay, well, A times B, that's an identity matrix. So this gives us E times an identity equals R times B, and E times the identity is just E. Okay, equals R times B. And let's think about what this thing on the right-hand side could look like. There are two cases. The first case is the reduced row echelon form. So I guess let me write it down here. Case 1. the reduced row echelon form has a row of zeros. So it has a row of all zeros. So if that's the case, then R times B, right? Imagine if you had a row of all zeros and you multiply by some matrix B. Well, multiplying on the left by this matrix R, remember what that does is it uses these zeros as coefficients to combine the rows of R, or the rows of B. But for this last row in R, the row that's all zeros, all these coefficients are zeros. So you get all the rows of B multiplied by 0 and added together. That means that we get a row of all zeros, like this. So this in this case, in case 1, we have a row of all zeros in R, but that means that R times B, right, here we had R times B, also has a row of all zeros. But R times B is supposed to be E. And E can't have a row of all zeros. The reason that E can't have a row of all zeros is because, remember, E is invertible. So if we took E times E inverse, this has to be the identity matrix. But if we had a row of all zeros in E, then when we multiplied it by its inverse, right, we just saw that when you have a row of all zeros, and you multiply on the left by something with a row of all zeros, you get a row of all zeros. But we just said that this product was supposed to be the identity matrix. So this can't happen. None of this can happen. This case 1, where R has a row of all zeros, that actually can't happen. So that doesn't happen. So case 2, for the reduced row echelon matrix R, is that there's no row of all zeros. Okay. Well, if there's no row of all zeros, then that means that there must be a pivot in every row. Okay. Right. If you don't have a row of all zeros, that means every entry or every row in R has a non-zero entry. But remember, in reduced row echelon form, the leading entry in a row has to be a 1. And so that means there's a leading 1 in every row. There might not be a leading 1 in every column. You might still have columns with no leading 1, but every row has to have a leading 1. Okay. Now for square matrices, this actually tells us something very nice. So if A times B is the identity, right, what we just showed is that the reduced row echelon form has a leading 1 in every row. But if your matrix is, if the starting matrix is square and there's a leading 1 in every row, that means there's a leading 1 in every column too. Because you can't have more than one leading 1 in a column, right? Every leading 1 has to be in a different column and a different row. So if there's a leading 1 in every row, there must be a leading 1 in every column as well. But if it's square and there's a leading 1 in every column in reduced row echelon form, that means that it's just the identity matrix. So what we've shown here is that for a square matrix, if there is a matrix B so that A times B equals A times B is the identity, then the reduced row echelon form of A is the identity. Okay. Sort of the, and you know, in this case, if A is square, then this means that B is actually A inverse. And that means that A inverse times A is also the identity. Right, here's B. And this means that this inverse matrix, the inverse matrix A, this is actually all of the row operations that reduce A to the identity matrix. So what we've really shown here is that for square matrices, so this is only true for square matrices, A being invertible is the same thing as the reduced row echelon form of A is the identity. So this is a different characterization of when a matrix is invertible. A matrix is invertible exactly when its reduced row echelon form is the identity. We sort of suspected that before because we thought, well, you know, when you are finding an identity by row reducing this matrix, if you can't reduce this left-hand side to the identity, then there is no inverse matrix. We sort of suspected that before, but we didn't know it for sure. Now we know for sure.